So this is an additional set of code that I've provided for you. It is experiment 2 from the simplified Coulombs law. And what I'm going to do here is really a lot different in some regards, but actually has most of the same base code. So all of this so far is the same. Now where things change a little bit is right here. So what I've done is I've set the charge of ball 2 equal to 0, which sounds like it's going to be pretty boring, because with Coulomb's law, 0 charge means it doesn't go anywhere. There's no force involved. But the other thing that I've done is previously you would have seen a delta t here, because what we're going to do is we're going to watch the progress of the first ball as time passed. Now what we're going to do is we're actually going to increment the charge of the second ball. So this one right here, and we're going to watch the effect that that has on the first charge. Now there's more complicated things that we could do with this, but I'm not going to do them. So we're just going to do a very simple one. I've changed the name so that I don't overwrite the spreadsheet from my first experimental set. I left all of these the same, I believe. And here I changed what was in the while loop. So I've made it so that instead of looking at time, I'm looking at the charge on ball 2. And once it gets up to 1 × 10⁻⁵ coulombs, which is actually a very large amount of charge, we're going to just stop. So I do my force calculation, and the force calculation has not changed at all since the previous set. But I decided not to do anything with the position and velocity, so I'm just going to fix both of the objects in space and look at the force that's being applied. And I'm doing this because really one of the things that we want to do is keep everything else constant but the thing that we're varying, and look at the effects it has. Now what you might do is you actually might vary the charge here, but put it, the charge of ball 2, but attach ball 1 to, say, a spring. So you could watch the deflection that it has as you vary the size of the second ball's charge. And that would be very similar to the Coulomb apparatus experiment that you saw in the YouTube video. So here's a very important line. This advances us through the while loop. Okay, so ball 2 dot q, so this is the charge on ball 2 now, is equal to the charge that ball 2 had before, plus how much it's changed. And then here I changed what we're going to graph. So rather than position and time, I'm going to graph the force in the x direction and the charge on ball 2. I changed the arrow scale. If you don't change the arrow scale, you're going to be in for a little bit of a treat as it gets to be a larger and larger force as the charge increases. I encourage you to try it. Maybe put in a 10 here or 100 and see what it looks like when you've completely screwed up the arrow scale, so that if it happens in the future, which it very well might, you know what it looks like and you know how to fix it. Just put in a smaller number. At the same time, if you can't see the arrow at all ever, then your arrow scale is too small and you need to make it bigger. So we've got this arrow 1 position. That's just where it starts, and we're going to just use the same thing that we had used before. And this is just me outputting those parameters into the Excel file. So I'm going to run this. Okay, and you can see that the size of the force is getting bigger and bigger and bigger, almost obnoxiously large at the end there. And this is what's happening to the force. Okay, and actually this is graphed a little bit out. They have charge here and force on the x-axis. Probably should be switched, but you still get the same idea. And this is exactly what we would expect to see with Coulomb's law, which is that the force gets bigger proportional to the size of the charge. So nothing terribly surprising there. That's going to be actually it for this one. You can of course look at the Excel file and play around with that. What I'm going to do for the next one is show you how to deal with a 3-body problem, but only focusing on one of the particles as being able to move. When we get to that, that's actually getting to the point where solving the problem that I'm going to show you computation by hand is not too daunting. But if we wanted to solve it for all 3 able to move, that would be actually almost impossible to solve by hand. And so what you do is you use a computer, and it's actually very easy to do it with a computer. So I'm going to get you started on how to do that type of a thing in the next video.